Hi, everybody. Welcome to our next round of gap year student talks. We have three talks today. The first one up is Vaibhav. Vaibhav, you want to go ahead and share your screen?
Okay. Yeah. So, hi everyone. I am Vaibhav. I will be presenting my work that I did during my 7-month internship at CERN this year. So, I was mainly working on Clad, which is a project under the Princeton University's compiler research group. So, I was supervised by Vasil and David. And the system as Project Clad was integrated with RooFit. So, we also had like meetings and interaction with the root ecosystem people, like mainly with Jonas Remser, who is working on RooFit. So yeah, this talk will be about Glad and its integration with root mainly. So I will be taking a top-down approach of the presentation. Like what we did essentially is that first I will give a brief intro of what RooFit is, then what was the issue, like and where does Clad come in to improve the things and the results that we saw after the integration. So a basic, like a brief one-liner for RooFit is just it's a statistical data analysis in the root ecosystem, and it's a C++ library. It's used for modeling and normalization of probability density function along with fitting of likelihood models. So you have some likelihood model that you derive from theory or some equations, and you have some parameters to fit in it. And it was the library which was also used in the Higgs boson discovery for the LHC experiments, and still, like it's one of the prominent libraries inside the LHC experiments. And this is one example of how the likelihood profile fitting might look like. So I'm not a physicist, but what I understand from this, like through my interactions with the root team, is that this is essentially fitting a likelihood model with mass of Higgs boson as a parameters, and each black dot is essentially a different minimization here. And we will talk more about this at the end when we discuss the results, but a basic intro of RooFit. So yeah, in RooFit, or essentially for any library that does fitting of any parametric model, you need to do some minimization. That you start with an initial estimate of those parameters and use gradient-based methods or Hessian-based methods to finally converge to the optimum value of parameters according to a loss function or reward type function, cost function. And it was seen that when we profiled the runtime of RooFit minimization, we saw majority of the time is going in gradient computations. So it was using MinWit2, which is one of the libraries inside CERN, and it was using the derivative methods like BFGS, but the derivative was computed using numerical differentiation. That if you have f of x, like you use f of x plus some epsilon, which is small enough, then minus f of x divided by epsilon on a high level. That's what was happening to compute the gradients. And this was done for each dimension. So you can see if it's a 1,000-dimensional function, it will require these numerical difference computation 1,000 times. It scales with the dimension essentially. So yeah, this was like the problem that we were seeing, that the gradients were slow. Can we make them fast? So one suggestion was to use automatic differentiation instead of the numerical differentiation. What automatic differentiation is? So automatic differentiation operates, or AD in short, I will use the term AD from now on, that AD is essentially you take a C++ program. This can be any Python program also, but Clad operates at the C++ layer. So it's a C++ program which represents a mathematical function, and you want to compute its derivative, or if it's a vector valued function, then it's gradient. So you want to compute a gradient of a function represented as a computational program or C++ program. So one way can be that you analyze what the code is doing, write it down as a mathematical equation, then use symbolic calculators like Wolfram Alpha, or do it manually by hand to compute the gradient, then hand code the computation that you obtain into a C++ program again. So this can be one of the ways that you do it, but you can see that it's not very scalable, that if the function is long or it has too many ifs and for loops. So AD operates at bridging this layer, that it operates between program to program, takes input as a C++ program, outputs a C++ program, computing, and the output is essentially the gradient of the input program, gradient or derivative of the input program. So yeah, like a crux of how AD operates is, for example, let's say you have these three statements in your code, which is essentially a chaining of multiple functions. You can represent this as a directed acyclic graph. And the point is that any function, anything that can be computed, can be written as a computation graph in a directed acyclic manner. And then computing the derivative is just applying chain rule over this graph. So if you want to compute the derivative of one output with respect to one input, so it's, let's say it's a partial derivative, a particular output's derivative with respect to a particular input. You just traverse the path on this graph from that input to the output and keep applying chain rule along the way. And for people who are more from the machine learning or deep learning background, they know that this is a generalization of what backpropagation is. Backpropagation requires or works when there is explicit modeling of the layers in neural networks, but it can also be generalized to any computation function. So what Clad is essentially that it does AD, but it does it at compile time. That while you're compiling the program, you can specify that this is the function I require to be differentiated. During the compilation, it will also create the code for the derivative code. So it will seem like this code was also part of your original code. And it's written as a Clang plugin because it operates at a compiled layer. So we need some functionalities from the compiler to get this done. And what's the benefit? Like, why not just use the existing Python-based or operator overloading based libraries? The main benefit that we get is that those libraries, because they operate at runtime, cannot handle control flow expressions and, for example, if conditions and for loops, because they rely on the path taken by the computation graph and just traverse that path back. But they can, for example, in control flow, there can be multiple paths that can be taken at different steps. And yeah, one of the other benefit is that now we have seen it in RooFit, and it's now default installed. Whenever you install root, it will come installed automatically, and it's there in Swan, so you can run it with your Python notebooks when you want to use your C++ code in those notebooks. So this was a basic intro of what Clad does, and this is a usage example. So how would you specify which function to differentiate? So in the main function, you can specify that it's not an invocation, I would say, because it's not happening at runtime. It's just a way of telling Clad that when you're compiling this code, look for the functions that I've specified inside Clad differentiate, that this needs to be differentiated. And you can also specify that I require the gradient or derivative to be evaluated at these particular points. So let's say you compile this code and specifying the Clad plugin along with it. You get the compile time output will just be the derivative code, which is given below. And if you also run this executable, you will finally also get the invocations of these gradient at the points you requested for. So you one of the main benefits that you can also get in this, that you can read the code that is generated for the derivative. So if you want to improve it somehow or modify it somehow, save it for later so that you don't have to do this again and again. This can also be one of the benefits. So now that we understand what Clad is, what RooFit at a high level is, and how they can be integrated with each other, we did some experiments where, like, my work was mainly improving Clad decent enough that we can see the benefits in RooFit. And this is the summary of the experiments that we did after this integration. Yeah, so this is essentially how the like the runtime efficiency improvements that we saw with integration of Clad and along with other improvements in RooFit. So the main benefit from Clad is the last part. So we see that with automatic differentiation enabled, this red part, which is the runtime profile of the minimization routine, this decreased by a lot, like more than 10x, I would say. And this yellow part, although it seems like the yellow plus red makes no difference, but this yellow part is essentially the just-in-time compilation time, that because RooFit operates at a computation graph level, that if you specify I want to minimize this likelihood, it creates the computation graph inside it. But Clad works at a C++ layer. It requires a program as an input. So at runtime, RooFit gives Clad the C++ program, compiles Clad, and then uses that derivative to do further minimization. So that's this jitting time of compiling the program again with Clad. Although this yellow part is a bit much right now, but this only has to be done once. So for example, if we come back to the graph that we saw in the beginning, each of this black dot is one minimization, but all of them require the same jitting code. So this yellow part would be common for all these invocations, and just the red part, the minimization runtime, is the one that's executed multiple times. So the thing that's executed multiple times is minimized by a lot, and the jitting time is amortized across all these minimizations. So we can see the direct benefit we can get from this runtime efficiency. And so two other experiments that we did to see how Clad will scale as the number of channels increases in the likelihood fitting. So we saw that with the channels, it was a linear scaling of how much Clad takes for the just-in-time compilation part, which is the part that we saw in yellow here, that how much time it takes to compile the likelihood model code and generate its derivative. And then for runtime part, we saw if a primal function, if the likelihood function takes, let's say, X amount of time, compared to that, how much time will the gradient evaluation that Clad generates, the code that Clad generates, the gradient code, how much time would that take? And we saw that it was within a factor of 3 to 5, irrespective of the number of channels. So that's good that the gradient code is not doing something which, like, completely arbitrary from the primal function. And even the memory consumption, that the memory consumption was also a constant factor from the primal function. And this is beneficial over the runtime frameworks that we have in Python, like PyTorch and TensorFlow, which store the entire computation that is happening along the way and then use that to traverse backwards. So along with this, like, this was the work that we had till the integration of RooFit and the improvements that we saw. But even after that, there were some improvements or possible improvements that are possible in Clad to further improve this. So one thing is that some minimization techniques require the computation of Hessians for as an initial step or as a seeding step. And Clad now supports, like already supported Hessian computation, but Clad now also supports computing only the diagonal entries of Hessians and not the complete Hessian matrix. And some further improvements that can be done in Clad, which will result in even further runtime efficiency, is analyzing the code and, for example, doing activity analysis to only traverse those nodes in the computation graph which are required for a particular gradient evaluation. So this is essentially like if you have a graph, not traversing the whole graph and only traversing the nodes which are on the path of this computation. And another thing that can be explored is parallelization. So if you have multiple parameters and the partial derivatives of these parameters can be split up completely separately and they can be run in parallel to further improve the efficiency. So we have a vector forward mode implemented in Clad, but we don't have a good integration yet for that in Hessians or RooFit. But yeah, that's something that can be explored further too. Yeah, this was my talk. Any questions or comments?
Thank you, Vaibhav. Any questions? No questions? Okay.
No, I was actually looking for my microphone.
Oh, sorry, Jim. Go ahead.
Yeah. So I'm particularly interested in the JIT time, the JIT compilation times
Okay.
of 35 seconds. Does the JIT use -02 or -03 optimizations?
So for all the experiments, we used -02, I think. Yeah.
Okay, so even with O2, it's something like half a minute of JIT compilation. You're right about the scaling, that it only needs to be done once and then gets to be reused over a large data set.
Mhm.
So in the performance plot, the bar chart that you made, couldn't you have made this more clear by using a larger sample, a larger data set in that plot on the left?
Large data set for?
In the plot on the left, that's, it's measuring some fixed amount of time. So it's, it's the output is some amount of time. So the input was some fixed number of data points.
Yes.
If you made that plot with a larger number of data points, then, you would have made the point that the JIT compilation becomes less significant. The JIT compilation time becomes less significant as the size of the job increases.
So I think what you're suggesting is that what I was talking about, that averaging over all these iterations and then reporting the average time so that the JIT time is
Or total.
amortized. Yeah.
Yeah, or total, just reporting a different plot. But still, it's that. I mean, that would make, I think, make the point stronger. But then there's still this point that 30, like half a minute is a long time for a JIT compilation. That's something I'm still trying to get my head around. Yeah.
Yeah, for this JIT compilation, this also includes the time that Clad is taking to generate the gradient. So this is something that can be improved other than just the O2 optimization, like the way Clad traverses this computation graph. This is something that we also, I was working by the end of the internship, that finding an optimal path of generating these gradients. For example, if there are 10 parameter inputs that you are computing the gradient against, can you somehow create a plan for this differentiation that there can be reuse between these multiple differentiations.
Okay.
Yeah,
Yeah.
this is something we were looking into improving.
Yeah, that sounds good.
Yeah.
Overall, this is great, by the way.
Thank you.
Alex, you had your hand raised?
Yeah, hi. Thanks for the nice talk. Yeah, just something to add for the sort of question of how long to spend and what is a long or a short time. Here, these models, the fit is relatively fast. I mean, this depends a whole lot on the kind of analysis that you're doing. The worst cases I've seen that we use in practice take many hours per single fit. I don't know how long these models would take to JIT compile. I'm not sure that like this is currently possible yet for sort of the worst kind of models we have. But in that scale, once you take hours, then even if you wait a few minutes, it's like absolutely nothing. And you will take hours per single fit, and you might need thousands of fits. So this depends a lot on the scenario. I think during sort of the optimization of an analysis, it's quite common that you will run one fit only, and then you move on, you change something. But also later on in the analysis, you will run hundreds of fits with the same setup. So I think the plot in that sense is quite fair because it shows with a different color what the relevant part is that scales or doesn't scale. But it really depends on the analysis and the kind of workflow step that you're at, which part you care about most, I guess.
Yep. Thanks, Alex.
All right. Thank you, everyone. Up next is Manasvi.
So hi everyone, I am Manasvi. I am currently a student, a master's student at Harvard University, and today I'll be presenting the work I did as a gap year fellow at Princeton University with Jim Pivaski and Yana Osborne. When I started the project, the infrastructure that connected the so I worked on extending CUDA kernel, the extending awkward array functions to CUDA. So when I started the project, the infrastructure connecting the CUDA kernels to awkward operations was already set up, and CuPy was used to handle the higher level functions. So the first task I did was to remove the obsolete kernels that were left over from awkward version 1. So after removing all those obsolete kernels, there were overall 144 CPU kernels that were remaining, and I had to convert these 144 CPU kernels to CUDA kernels. But there were 42 of the CUDA kernels which were already automatically implemented because they were embarrassingly parallel. It was very straightforward to parallelize them. So after that, the main task was to convert the remaining trickier 102 CPU bound algorithms to CUDA algorithms to make them parallel. And another issue was that due to lack of testing, there was some errors even in the already implemented 42 CUDA kernels. So due to the way the awkward 2.x architecture was built, it introduces an indirection as we move from the upper to lower layers. And because of that, awkward has no direct dependency on CUDA. Users can still use the CPU backend without installing CUDA. So they don't even if they are not using GPUs, they don't have to install anything. They can directly use pip install CUDA. So and if the users want to use the GPU functions, they can still use the same installation of awkward. They just need to have CuPy installed in their system. So I categorized the CUDA kernels into several categories in order to group them according to the type of algorithms that needed to be used. So even in the 102 kernels, there were a few kernels which were found to be embarrassingly parallel, and it was very straightforward to parallelize them. There were some kernels that were calculating cumulative length or max or sum, which required a certain algorithm to just to calculate the cumulative, like the cumulative scans. And there were some kernels that were using the variable length inner loops. And the major chunk of the kernels that I worked on were the reducers. So there were these general reducers like the sum, max, min, argmin, prod, and there was the complex equivalent of these general reducers. And also there were combinations and segmented sort and arc sort. So I'll discuss the most interesting of these kernels, which were the reducer kernels. So, so the naive way to solve the problem that we had for reducer kernels. So basically, in reducer kernels, we like instead of calculating the sum of the entire array, we needed to calculate the sum of each segment, which were defined by the parents. So if you see the example here, the greens, like if we can say that the greens represent to parent 0, and the blue represent to the parent 2, and the pink represents parent 3. So the naive way to approach this problem can be that we can assign each segment to one thread. And like for thread 0, we can assign a particular parent and so on. But this approach has a problem because it creates load imbalance. So each lane in a warp must wait for the entire warp to finish before returning. So in case we have threads assigned to a long segment, and there is another thread which is assigned to a very short segment. The long segment will stall the neighboring threads, and the shorter segments will have to wait for the long segments to finish. So in order to improve this approach, we can use the load balance approach. So in this approach, we can assign a fixed number of elements to each thread, and then we can sequentially accumulate the consecutive elements. So like as compared to the previous approach, we can just like if in this example, we are taking the fixed size of 3, and we are just distributing like just making chunks of 3 for each of the threads, irrespective of the segments that we have. So in this case, we can have a segment that is divided into multiple threads. So we can store the partial reduction as carry out values. And when the last element of a segment is encountered, we can just clear the accumulator. And after that, when we have all the carry out values, we can just reduce the carry out values and add them to the partial reductions to get the final results. So here is an example. Like we use the Hillis-Steele algorithm to do the partial reductions. So basically, Hillis-Steele algorithm is an algorithm which uses parallel computing by dividing tasks into smaller chunks that can be processed independently by multiple GPU cores. So this divide and conquer approach allows each core to handle only a portion of work, which is followed by a reduction step, which can be used to combine the partial reductions to get the final output. So this algorithm optimizes memory by minimizing the data transfers, making it highly efficient and scalable, and which is ideal for large-scale computations on GPU. So I modified this approach in 2 ways. So the first way I modified it was to account for the segmented scan that we need to do for the problem. So the Hillis-Steele algorithm usually computes the global prefix sum for the entire array. But in this approach, we calculate the sum separately for each segment of the data and where the segment is defined by the parent. So we only calculate the sums for each parent, not the entire array. And the second modification that I did was to account for the load balancing approach. So the array was divided into fixed size chunks. ignoring the segment boundaries, so that we can ensure that the workload is distributed evenly across the processing units. So as you can see here, so we have used size 3 chunks, and we have the parent 0, which is entirely in the first chunk. And in the second chunk, we have the parent 2 and part of parent 3, and the remaining elements in the last chunk. So we can see that the parent 3 is divided into chunk first and second, and the 0th has only the 0 parents. So this is just an example to get a better idea. So as you can see that we are just calculating the segmented sum for each parents, but within the boundaries of the fixed size chunks. So after the computation, we can see that the partial sum for parent 3 is split across 2 chunks, which is stored as carryout values. So in order to get the final results, we need to recombine these partial results. So for that, we use a condition that we will only combine the pairs for a particular parent. So we just check if in the carryout values if the parents are same, and if the parents are same, we just combine those values. And for the final result, we just take the last value of each event. So like here we just combine the partial sum from the second chunk and the third chunk, and we got the final values. So this is just an example how CPU and CUDA backend uses the awkward functions. So this is a simple example of a list offset array, and how we can use that for a CPU backend and a CUDA backend. So the only difference that we have for the CPU backend and the CUDA backend is just passing the array that we have to the CUDA backend. By default, the backend is specified as CPU. So the user only needs to send their array to the CUDA backend, and rest they can perform the same operations without any special syntax. So besides adding the kernels, the major part of my work also included testing of the kernels. So I extensively worked on improving the testing infrastructure for all the CPU, CUDA, and Python kernels. I noticed that many of the already implemented CUDA kernels were not being tested. And after generating the test, I found there were some major issues in some of the kernels and fixed their implementations accordingly. Integration tests were added for each awkward functions, which helped in identifying and fixing the issues in the Coupa infrastructure. So just to get in a bit more detail, I improved the Python script that was used to generate the role-based test in awkward for all the kernels in order to add custom unit test in a JSON file, which was used to generate the Python test. I focused especially on identifying the edge cases and adding the custom test to increase the code coverage. Also, the test generation script only worked for certain types of parameters, and it needed to be fixed to work with pointer to pointer, for example. The test generation script only checked the CUDA C++ kernels, but it was important to test if these kernels were being correctly used by awkward functions for the CUDA backend, so that we get the same results as the CPU backend. So like similar to the example given here, we had integration test to check if a certain awkward function was working as required, like as same as what the CPU backend works for the CUDA backend, and we just tested for that. So there were some other tasks that I worked on, some minor tasks, which were like adding the kernel specifications for the Python kernels, which was just a like very simplified description of what the kernels do. And I also fixed some issues in some of the CPU kernels, like very minor issues like the nomenclature or some memory access issues. I also added, there were some missing kernels for Boolean type because it was only working with the other types and not the Boolean types. It was found during testing. And I also removed some obsolete functions in dead code that was from awkward 1.x. So just to summarize, right now, almost all the major CUDA kernels are implemented. And we have enhanced test coverage for CPU, CUDA, and Python kernels. And the users can now use awkward functions in GPU to do their analysis. And this is just a graph of, just to summarize my work during the Gap Year Fellowship. Thank you. Any questions?
Thank you, Manasvi. Alex?
Thanks. Yeah, it's very nice to see all of this work on making all of this work on GPUs. I'm curious about if you have looked at or how it would compare to the JAX backend and if that actually works on GPUs or not. Because sort of like in the talk now, I was wondering, is this complementary? I mean, I know sort of technology-wise, it's a different approach, but how does this compare otherwise to running with the JAX backend, if that does run on GPUs indeed?
As far as I know, the GPU, the JAX backend doesn't have the GPU support, at least right now. Because there were some missing areas for the JAX implementation. When I was working, I don't know if there has been any update.
Yeah, I think that if you had a JAX device array on where the device is a GPU, I think that would work. But the JAX backend in awkward array is very limited. It was very difficult to get anything from JAX to work in awkward array. I think right now we have basically mappers and reducers, ufuncs, and the reducer functions. And then for the reducers, we had to go into the lax, the special functions in order to find something that would actually do segmented reduction. Yeah, exactly what Manasvi was showing here. The thing about the GPU backend is that it aims for completeness. That when the last, 10 kernels need to be done or something. When those are done, then, and there are no bugs, then 100% of the awkward operations you can perform on a CPU, you can also perform them on a GPU. That's what we're aiming for. And I think the JAX backend will never do that.
Okay, I see that. That's very helpful. Thanks for clarifying.
Any other questions for Manasvi? All right, thank you, Manasvi. Up next is Saransh.
Hi everyone. I started at CERN or under the IRIS-HEP group to work on automatic differentiation, or the JAX backend of awkward, as we were talking about at the end of the last talk. But soon that work expanded a bit to include other parts of the analysis pipeline as well. So at the end, I just ended up calling my project or final report that I submitted at my college as computational upgrades to the HEP analysis pipeline for future LHC runs. And this was supervised by Jim. Okay, so I'll start talking about my initial project, enabling automatic differentiation for the scikit-HEP ecosystem, or more precisely, when I started my work, it was already implemented for the statistical part of the ecosystem. And also JAX backend of awkward was already in place. but my major task was to clear the existing bugs and get the backend up again, because it wasn't being used by physicists a lot, so there wasn't a lot of attention going on that part of Awkward. And once that was done, Coffee and Vector had some issues related to JAX. Those were resolved as well. Okay, so the motivation behind this work, this is how I understood why this work was important, or why particular parts or individual parts of a pipeline should be differentiable instead of the whole pipeline being differentiable at once. So physicists require tuning of hyperparameters, as Weber pointed out in his slides, in analysis pipeline. And sometimes they want to use arbitrary functions as a loss function in the middle of the pipeline. And to tackle this, each part of the pipeline must be individually differentiable, so that they can pick any loss function from the middle of the pipe, any function from the middle of the pipeline, and use it as a loss function. So for example, a p-value function can be used as a loss function for tuning some of the hyperparameters. A really nice resource I found on this while I was working is Nathan Simpson's thesis, where he worked on two libraries under GradHEP, Neos and Relax, which basically add AD support for the statistical part of the pipeline, of scikit-HEP pipeline, and also some common operations like I know they have support for some sort of histogram and operations like cut. I also met Nathan at IRIS-HEP. It was really nice to catch up with him there. Okay, and when I started working on this project, Awkward's JAX backend already existed, but it had some known bugs, and these bugs were basically blocking the integration of Autodiff in ADC in the analysis grand challenge, or at some point they blocked it, and then the development of this part was stalled. Yeah, after the blockage, the JAX backend's development was stalled to prioritize other work. And as Jim pointed out, the backend was not, it wouldn't allow differentiate any arbitrary awkward code, but specific functions and specific reducers. And even those reducers were, and they still use the lower level JAX API to work on segmented arrays. So this is how the backend works right now. JAX provides a really clean way to extend its API to any arbitrary data container. All you have to do is tell it how to flatten the data container and how to unflatten the data container. Once that's done, it basically automatically allows you to perform JAX functions on it. But given that awkward arrays are not flattened arrays, they're ragged. In the code, they're flattened first, then awkward slices, ufunction behaviors are handled. After that, it becomes an interoperable layer between awkward arrays and JAX's device arrays, and these things are differentiable. Once the differentiation step happens, the arrays are reassembled and are provided to the user, so they're unflattened. So if a particular awkward array looks like this, only the NumPy array part is provided to JAX, and specifically the lower level API of JAX. So if I remember correctly, it was segment_OPS something module that had those particular functions that can work on windows of arrays and not the entire array itself. This is mostly how the JAX backend looked like when I started. You can register JAX and perform popular JAX operations such as JVP, VJP, gradients, and a few other operations through awkward arrays and some of the reducers available in awkward arrays. What I did was made a few more reducers compatible with JAX. So these were awkward.main and awkward.count, and also arbitrary binary operations compatible with the JAX backend. So for instance, now you can differentiate a function that would look like this, that's chaining awkward reducers and using arbitrary binary operations on the arrays. You can use that for the supported JAX functions such as grad, VJP, and JVP. And also, when I started, there was JAX was clashing with number. JAX cannot differentiate number JTET function, but now it does not at least clash with number. So you can use number and JAX together inside your code base. It still clashes with Dask, and there was an issue opened in Coffee about it, but then there were no plans of, or there were no discussions, no further discussion about how to handle Dask and JAX simultaneously in a single code base. And also, once the awkward issues were fixed, the downstream issues were fixed without much efforts. So all the code that was being logged in Coffee because of JAX issue started working again. So you could use functions like ak.2 backend to convert Coffee vectors to the JAX backend of awkward, and everything would work. So finally, awkward array, Coffee, and vector are not differentiable without any known issues. The existing issues have been resolved, and this has paved the way for introducing automatic differentiation in AGC. And I had a nice long chat with Lino at PyHepDev about him possibly picking up auto diff in AGC sometime this year or the next year. Okay. Yeah, so this talk would mostly be structured like this. I'll be talking about a single mini project, its motivation, some of its working, and how the results look like right now. So the next thing that I worked on was preparing Victor for future LHC runs. And most of these projects were technically going on simultaneously. They were not put sequentially one after other. Okay, so the motivating factors behind this particular mini project was that several design issues had popped up in Vector following its adoption or the talks of its adoption in Coffee. The new JAX backend of Awkward, Dask's adoption in analysis pipeline, and so on. Physicists had started using Vector possibly because of the talks that were going on in Coffee, and they started pointing out a lot of issues or a lot of things that could be better or that would suit them better in Vector. And all the work that was done changed Vector to either solve bugs or adapt the library to physicists' requirement by adding new features or new backend supports. Yeah, so the fixes and features in vectors, the list is large or huge, so I couldn't really add examples here, but all of them are available in the changelog of Vector, and they would link to the specific PRs that are available. But I've highlighted some of the fixes or the features that would be a possible breaking change for people, or they're the important ones that went inside Vector releases. So in V1.2, we basically created a uniform thing or a uniform scheme for promotion of geometric dimensions of vector to demote or promote it that would follow the rules that Coffee had already. Also, Vector, I updated Vector to be able to make it easy to inherit vector classes to other modules. That started with Coffee because Coffee wanted to inherit vector classes and extend them. But while doing so, they discovered a lot of bugs in that because no other library was at the moment doing it, and we didn't have any tests for that. V1.3 had some more changes regarding the promotion and demotion scheme. Also, a like method to automatically convert vectors from one geometric dimension to another by taking reference of another vector. And now it became like the vector became strict on that promotion and demotion scheme. So it would error out if you would try to add, let's say, a 3-dimensional vector or a 4-dimensional vector, 3-dimensional vector with a 4-dimensional vector. V1.3.1 introduced support for Dask awkward. So you can now pass in Dask awkward arrays in vector constructors. And it also made momentumness infectious. So before this, it was if you have a momentum vector and a generic vector, the result would be a generic vector. But now, even if you have one momentum vector, it would convert the output. It would output a momentum vector instead of a generic vector. And a few more fixes for inheriting vector classes. V1.4 introduces SymPy backend, which is a whole another project that I'll be talking about, and also a few more features and fixes. And V1.4.1 introduced full NumPy 2 support. This was being blocked by SymPy backend. More specifically, SymPy's numerical computing library, MP Math, if I'm not wrong, that did not support NumPy 2 as soon as it was out. So we had to wait for a few months or a few weeks to support NumPy 2 completely. And then a few more fixes and maintenance and documentation tasks. Finally, I added support for one new backend to vector, SymPy, and extended support for two more backends through Awkward, that is Dask and Jax. A lot of bug fixes pointed out by physicists using vector. So that means physicists were using vector, and that was a good news. A few new features were added too, and a lot of quality of life upgrades were added that were requested by physicists. And vector crossed 1 million downloads. Okay. After vector, or simultaneously, I was working on migrating coffee to vector, and most of the changes that happened in vector were because of the discussions that started at coffee. The motivation behind this work was that coffee's vector modules predated scikit-hep/vector, but now that vector had achieved a lot of maturity, it made sense to migrate coffee's internals to scikit-hep/vector, similar to how it had been done with other coffee modules, such as the histogram module of coffee, coffee.jitters, if I'm not wrong. And the vector module, the vector library at scikit-hep was now much more sophisticated and functional than coffee's vector subpackages and vector subpackage, and it included support for third-party libraries as well, such as Jax, Dask, and SymPy. So the idea behind the whole migration of coffee was to keep the user interface exactly the same so that users don't have to switch their code a lot, but instead change the backend of all the vector manipulation computations. So instead of just telling users to switch directly to scikit-hep/vector, inherit vector classes, extend them, and provide them the exact same interface that they're using, but instead of using methods written inside coffee, use methods from vector itself. Yeah, so the working included, or the methodology included inheriting these vectors or vector classes, or pseudo inheriting these vector classes, then registering the awkward and numpy behaviors. For this, a new function was added to awkward, a utility function called copy behaviors. This resulted in coffee vector classes with the exact same interface, but with a different computational backend. And then these coffee vector classes, included the candidate vector classes, could be inherited to provide more specialized classes such as Jet, Muon, or other such classes. So this is how the results of this mini project looks like. If you create a normal coffee vector through a root file, or you manually constructed, you won't see any difference. But if you look at its MRO, you'll see vector classes popping up in the inheritance diagram somewhere. And this is how everything's happening. On the upper layer, it shows coffee, but internally on the backend, it's using vector for almost everything now. And this has also, the efforts have also like unified the vector manipulation things in scikit-hep. So before migration, coffee vectors and scikit-hep/vector were slowly brought closer, so that for the final migration, just the variable names were swapped out, and it automatically started working in coffee. So you can see, for if you use vector and if you use coffee, creating vector has the exact same interface with only some minor changes. So finally, migration changes have been released already, and they were a part of Coffee V 2024.8, the August release. And users can expect Coffee to entirely scrape its vector module and depend on scikit-rep/vector by the end of the year. I think Coffee is still throwing a warning for this. There are plans, but I don't know how much I will be involved in this. Okay. The next thing that I did was implement non-uniform rebinning in Boost histogram. The motivation behind this thing was that Boost histogram allowed rebinning a regular axis to another regular axis, but it did not allow rebinning a regular axis to a variable axis. And this was something that had been requested by a lot of people in different places, and this had been already formalized as a part of UHI, which was also being adopted, which Root also plans to adopt sometime this year or the next year in a certain period of time. And all of these issues were gathering a lot of interest. I did implement it, and this is how it works right now. If you pass a particular factor to the existing rebin class of Boost histogram, it will run the existing rebinning algorithm in C++, handle slices, and output the required histogram. But if you pass in groups, or as we'll see ahead, you can pass a list instead of a factor, instead of an integer, to go from regular access to a variable access. This would run the rebinning algorithm in Python right now in the get item method of the histogram class. We'll handle slices and everything, and then create a new C++ object for variable access, pass this C++ object to the C++ histogram, and then pass that C++ histogram to pass the Python bindings for that to the user. And this is how it looks like right now. So you create the histogram normally. Now, instead of just passing in rebin, like this is something that you could do with Boost histogram. Before I started my work, you could pass in a rebin with a factor that could go from a regular access to a regular access. But now what you can do is, instead of passing a factor, you can pass in a group, and that would work exactly the same with the same API, but would instead go from a regular access to a variable access. One caveat in this is that all the bins must be accounted for, so you can't shrink the axis of a histogram right now. The sum of this must be equal to the length of the axis. And similarly, you can do it with you can combine it with other different APIs of Boost histogram, or scale it to a histogram of multiple dimensions. So yeah, this was released as a feature in Boost histogram v1.5. Okay, I'll try to go through it quick if I'm running out of time. But the next thing that I worked on was adding a SymPy backend in Vector. The motivation behind this was to allow theoretical physicists to use the same software for certain tasks that is used by experimental physicists. And since SymPy vector classes would operate on SymPy expressions, it would allow us to use any arbitrary SymPy function on vector manipulations. But also a major motivation was that vectors compute functions that operate on data containers, operated on data containers, and they still operate on data containers. And this behavior was tested using uncompiled 6 on Python 3.8 in vector CI. But once Python 3.8 reaches its EOL, or end of life, we won't be able to test this behavior anymore. And the SymPy backend will allow us to continue the testing of this behavior, because once we know that the SymPy backend, the test for SymPy backend is working, we'll know that the compute functions are still working just on the data containers and not on any numerical data. This is how the backend works right now. It essentially runs very parallel to the numerical backend. So the API is not very different from the numerical backends, but internally it uses a shim layer to map the SymPy functions to NumPy functions. And yeah, this is how it looks like right now. So instead of just creating a momentum object. So instead of creating an object type momentum vector, you can use a SymPy type momentum vector. The API is exactly similar. Instead of passing the numerical data, you will pass SymPy.simple, SymPy symbols, or SymPy expressions. And you can perform any given vector method or functionality on this particular vector. And it'll all be done on the data containers instead of the numerical data. But you can also use SymPy functions such as simplify on these expressions, because these are pure SymPy expressions, so any SymPy function can be used on it. And then you can evaluate substitute values evaluate the expression to see if it matches with the existing numerical backends. There would be a slight error because the numerical backend is different, but it's the same for a few decimal places. The SymPy backend has already been released as part of Vector V 1.4. There's a small caveat that operations on SymPy vector are only 100% compatible with the numerical backends if vectors are positive time-like. For space-like and negative time-like vectors, not all of the operations might give correct results. And I'll be presenting this at CHEP 2024 as a poster, and I've already presented the SymPy backend at PyHep this year. Okay, this was the last thing that I worked on before my fellowship ended. The last 2 months were spent on creating a new package for histogramming on GPUs. As Manasvi presented her work on awkward arrays, putting awkward arrays on GPUs, it garnered a lot of interest from physicists, especially from coffee developers. And though this work was being carried out in full throttle, there were more pieces that were required to perform a complete analysis of high energy physics data on GPUs. And one of the major missing pieces was the ability to generate and manipulate histograms on CUDA or on GPUs. So this is how the package right now works, or the API that it implements right now. It implements a subset of features of Boost histogram using QPy. And it's completely independent from Boost histogram right now, so it does not inherit the histogram class or the hist class from any of the libraries. It currently implements the regular and variable axes and some methods for these axes, such as edges, centers, index, and others. It implements a histogram class, and this histogram class includes the fill method, which can be a weighted fill, and it includes something called as NaN fill, which was available in coffee hist classes, but I don't think it's available in Boost histogram and hist. But Lindsay decided to keep it within CUDA histogram. There's also simple indexing with slicing, and you can extract values and variance from the histogram class. It also allows users to detach the generated GPU histogram to CPU using 2 methods, to Boost and to hist. So the idea behind the package was that the users will create a CUDA histogram, then perform the fill operation on GPUs, and a few other operations such as indexing or a simple slicing and simple indexing. And for every other complex UHI operation or any other operation offered by Boost histogram or hist, they would simply detach the histogram and convert it to CPU, to Boost histogram or hist, and then continue performing other UHI operations on it. So we identified that the main thing that we wanted on GPU was the filling function and not the other UHI functions. It has a lot of differences, not a lot, but some tiny differences that you'll notice with Boost histogram and hist API. So one of the big ones is that it has NaN flow. It accepts only QPy arrays. Underflow is indexed as 0 and not -1. And then there are some custom data structures or classes within it that are returned instead of just returning a NumPy array. and complex things such as interpolation is not performed right now. These were the future goals of the package, or the goals that I wanted to implement, but I didn't have enough time to. One of them is categorical access, and the other one was to improve indexing, or the get item method, to exactly match Boost Histogram's API. And I didn't have a GPU device, so these are screenshots from the README of CUDA histogram right now. So you can create a object or histogram similar to how you would create in Boost Histogram or Hist. You can fill these with QPy arrays instead of NumPy arrays, and the value that it would return would be of type QPy array and not NumPy array. And setting flow bins to true would return underflow, overflow, and non-flow. Then these are some of the differences from Boost Histogram's API. So indexing should be within the bin interval and not any arbitrary integer indexing. It should not be integer indexing. It should be a value within the bin interval. Then it returns interval class instead of just returning a QPy array or NumPy array. Yeah, most of it is available inside CUDA histogram's README. And things like interpolation that's not performed, or indices must be in the range of bin edges. And finally, you can convert it into the regular Boost histogram or Hist class using h.toBoost or like the toBoost or toHist methods, and they'll convert everything to NumPy arrays. So finally, this has been moved to scikit-hep at pyhep.dev, and v 0.1.0 is available on PyPI right now. Okay, finally ending everything. Right now, after completing everything, I'm writing a JAWS paper for Vector, preparing for CHEP, and grad school of applications are opening soon. I've joined UCL's ARC as an assistant research software engineer, and I'm planning to still maintain Vector and CUDA histogram, and I'm already answering some issues and discussions that are popping up that were related to my issues. The good thing is that I get 5% time here at UCL to spend on research software outside of my official work, so I can dedicate that to open source ecosystems such as scikit-hep. Okay. Final thanks for funding these projects to IRIS-HEP. I can definitely not end this without thanking Jim. He was an amazing supervisor, and I absorbed a lot of knowledge from him in this short period of time. And then there were a lot of other incredible people that I was fortunate enough to work with, given the nature of my work. And I'm really thankful to each one of them and for all the discussions that we had. Okay.
Thank you, Saransh. Nice talk. Any questions or comments for Saransh? Alex?
Hi. Yeah, no question, but as a comment, I mean, thank you very much for all the work. And I mean, in particular, I know here because you helped close multiple issues that I've opened. So, I mean, I'm very grateful for all the progress on the various projects that you made in your project. Thanks.
Thanks.
All right. Well, thank you to all the students for your nice talks. That's it for today. Thank you all for coming. So long. Bye.